Okay. All right, so let's see, we're gonna go over quiz 7. Okay, so this is what we took yesterday. We went over this one yesterday. Okay, so quiz number 7, question number 1, increase the number of capacitors in parallel. Okay, so the formula for calculating the resistor, the capacitor in parallel is C total equals C1 plus C2 plus continuously until to the end. So that means if you add them in parallel, you will increase the total capacitors. So the answer is C as in cat for number 1. Number 2, the two capacitor in parallel, one is 1 microfarad and one at 3 microfarad, have a combined capacitance of, okay. So we take the 1 plus the 3, so that's total be 4. So the would be 4, the answer is B. So that's 4, this one is 3. Okay, so the answer is B as in Bob for number 2. Number 3, increase the number of capacitor in series. Okay, so when you increase, when you add in series, it would decrease in value. Okay, so you use the inverse formula, and so you come up with so that would decrease the capacitor. So if you decrease the capacitor, you would increase the impedance, the XC, if you increase the resistance on XC. So therefore, you're going to be decreasing your current. So the answer is B as in boy for number 3. Okay, any question number 1, 2, or 3? Okay, no question. Next set. Okay, a capacitor is ability to hold electric charge. Yeah, that's what a capacitor do. Just they hold the electric charge. So the answer is C as in cat for number 4. Number 5, the total capacitance of 2 capacitors in series. So therefore, if you add them in series, it's going to be decreasing in value. So always less than the smallest individual capacitor. So whichever one it is going to be the smallest one. So the answer is B as in boy for number 5. Number 6, increase the frequency of the signal applied to capacitor. Okay, so capacitor, so this XC would depend on the capacitor and depend on the frequency. So if you increase the frequency, you would increase XC. Increasing XC would decrease the current. Wait a minute, let me see. No, increasing the frequency would decrease XC. Decreasing XC would increase the current. So the answer is D as in dog for number 6. Okay, any question number 4, 5, or 6?
Yeah, quick question.
Yes, Nicholas.
XC stands for impedance, or is that capacitive reactance, or is that
yeah, this one represents capacitive reactant because we only did only deal with capacitor.
Okay. Cool.
Okay. Sounds good. Okay. All right. Any other question? Okay, next set. Okay, a capacitor allows DC current to flow only when it is, actually it happens when it is charging and as well as when it is discharging. So the answer is A as in apple for number 7. Okay. You can pulse it, you can push it on the DC, you can push it and then so get that to charge up the capacitor, and then as soon as you release it, it would discharge whatever that was charging into the capacitor. Okay, so the answer is A as an apple for 7.
Hey Sam, I don't mean to be a bonehead.
Go ahead, Joe. Go ahead and unmute yourself, Joe.
Okay, they talk about capacitors block DC, because I was Googling that. I mean, just out of conversation, and they give the impression that capacitors only discharge through AC. Or maybe it's the way they wrote it or something.
Only what in AC as well as in DC. You can charge the capacitor once it hit the maximum, then it will cannot be charged anymore. Once it hit the maximum, they will block the DC from going anywhere else. Okay, but if you have a load resistor, it would discharge the capacitor would discharge that whatever was charged.
Yeah, that's what I was thinking too, because I was trying to find something that said, you know, it discharged through DC as well. Well,
yeah, if you have a load, yeah, with a load, it will discharge from the capacitor.
Yeah.
The capacitor will charge and it will discharge as long as you have a load resistor at the end.
Yeah. All right.
Yeah.
Hey, thanks a lot, Sam.
Okay, you're welcome. But on the AC wise, it worked automatically because it's always changing all the time. DC, we have to pulse it on the when we push it and it turn it on and it goes into charge the capacitor right away. And once the capacitor full, it will block the DC from doing it. It would not keep on charging. Once it's full, it stopped. Okay. And then once we release that, and then if that has a load resistor, it would discharge that, the capacitor would discharge the voltage that was there into the load.
And not to beat a dead horse to death, but the resistor, it's at the same value as the source voltage, but then as the charging stops, the current and everything on the resistor starts going down, correct? And it goes over to the capacitor.
Yeah, the capacitor would charge at the beginning. The current would go really fast. It would go up really fast, as you can go up to 63% at 1T, and then after that, it's only go from here to here. It's only about 23%. So it's keep on decreasing
So it gets
until
5
it
time constant.
yeah, until it reach 5-time constant. That's it. That it would stop. But with the AC, like I said, AC changing all the time. Therefore, it can charge and discharge all the time, because once it goes into the negative side, it would discharge, and when it's positive, it's going to charge. But on DC, we have to pulse on the turn on the switch and then release the switch. When you push the switch, it charges the capacitor, and then when you release it, as long as you have the load, it would discharge that into the load.
Okay, thank you, Sam.
You're welcome. Okay, so that's A as an apple for 7. Okay, for the A, the current flow through inductor. Okay, so anything that flowing through inductor, the inductor has the current leading, the inductors, current the inductor lags the voltage by 90 degrees, and the voltage lead the current by 90 degrees, and the voltage lead the current by 90 degrees. So the answer is C as in cat for number 8. Number 9, the adding inductors in parallel to an RC circuit. So in parallel, so inductor in parallel, it's going to be the more that inductor you added, it's going to reduce or it's going to be equal to the smallest of the smallest inductor. So therefore, the inductor is going to be here. So when it's getting smaller, so this is decrease here, and so there decrease XL. Decreasing XL would increase the current. So the answer is B as in boy for number 9. Okay, any question number 8 or 9?
I just had a question about what we were talking about on 7.
Okay, on 7.
Yeah, so capacitors automatically get discharged during a negative signal under AC current and then charged under positive. Yeah,
so when it's positive, it is charging right here. It's charging. When the AC reached when the AC is starting to moving toward coming back down on the slope, it would start to discharge from the capacitor.
You're talking about the negative half cycle.
Yeah, on the negative half cycle of the AC signal. Okay. So one is charging, and then after that, one is so the positive. When it goes to the positive, moving to on the positive cycles, it's going to be charging, and then when it's going to negative cycle, it's going to be discharging. You follow, Nicholas?
Yeah.
Okay, good. All right. All right, any other question? Number 6, 7, 8, or 9? Okay, everybody's clear? All right, next step. Okay, the equation XL equals 2 pi FL is valid only for, okay, only for sine wave only, because if you're taking a like square wave, they can have so many frequent, you're going to have a lot of frequency, like Mr. Pham said yesterday, you have so many harmonics in a square wave, so therefore you can't use that to use a calculation. Only pure sine wave you can use to do the calculation of this F used as a frequency to calculate that, okay? Because on the square wave, there's way too many frequency, and all others AC waveform, no, because then you have the square wave, the triangle wave, that also make a whole bunch of consists of so many of the sine wave in there also. So you need just a pure sine wave only. So the answer is D as in dog for number 10. Okay, for 11, the inductive reactant depend on, okay, it's going to be, so the inductive reactant, XL equals 2 pi FL. So it's depend on the frequency, and it's going to depend on the inductant. So the F and the L. So frequency and inductant. So the answer is C as in cat for 11. Okay, for number 12, this one's sort of a little bit of tricky, question, a little bit, okay?
Yeah, because of the word function.
Exactly, so.
And there could be more than one thing under function.
Yeah, so say what control on the generator determine the type of output waveform. Okay, mainly we look at whatever the function here, what we set up, either the triangle sine wave or square wave or positive edge or negative edge cycle. So therefore, first is you need the function. So this is the function here. You set it up so you can get, depending on what kind of signal. Do you want AC signal, or do you want a square signal, or do you want a triangle signal, or square wave signal? And so that's what you set up. You use this function signal here. Okay, so that's B as in boy for number 12. Okay, so in the other one, on the other generator, you also have it. So you're using this one right here on this corner here, if I can enlarge it a bit. So this one does not have a label like here, the function, but you push one of these buttons here. So you can get a sine, square, or a triangle. Okay.
Did that, what did it say for the question? Did it ask about the scope or the generator?
No, they said what the type of output waveform. So waveform, so this is the waveform that you can set up. Okay. You can set up a triangle, you can get up sine, you can set up a square or leading edge or negative edge. Okay. So this is positive rise and negative rise. Okay. So this one is for this one, this other generator, you can only have 3 output waveform that you can generate: sine, square, and triangle. Okay.
Okay.
All right. Okay. So, any other question number 10, 11, or 12? Okay, everybody's good. All right. Okay, so the control that adjusts the frequency on the AC generator or the frequency. And so the other thing is the range. So you use this frequency here to adjust. Now this one depend some of the other one, some of the older oscilloscope, it's called a multiplier. Okay. Oops. Let's see. Okay, can everybody see that? Okay, so this one normally they consider as a multiplier, but here it's labeled as a range. Okay, So you take this one here, so 1. So if you adjust this knob here, the frequency to 1 times 1K here would be, that would be 1 kilohertz, okay? So this is sort of what it referred to as a some of the older oscilloscope labeled this as a multiplier. So, but this one labeled as a range. So this is the knob that we're referring to. Okay. So that's so the answer is B as in boy for number 13. Okay. All right, number 14, you can determine the time constant of an RL circuit by using the equation. Now, this was not covered in the lecture, but it is covered in AC 1 lat volt, okay? So they said time constant equals L divided by R. So the answer is B as in boy for 14, okay? Okay, number 15, in the RC circuit have a time constant of 3 milliseconds. The capacitor will be fully charged, assuming there's no initial charge in it. Okay, so at 1T, it would 3 milliseconds. At 2T, so 2 times 3 would be 6 milliseconds, would be go to 86. At 3, that would be 9 milliseconds. So times that would be at 95%. At 4T, that would be 12 milliseconds. That would be 98.2%. And at 5T equals 15 millisecond or 99% or fully charged. So the answer is D as in dog as for number 15.
I guess the key to that one, you have to remember that fully charged is referencing 5 time constants.
Right.
And 5 times 3 is 15.
Correct. 5 times 3 is 15. So that's total 5 times. Okay. So it takes you 15 milliseconds to fully charge that capacitor. So any question number 13, 14, or 15?
I got question on 14.
Okay, Nicholas, go ahead.
If that was a capacitive circuit, would it be time equals C over R?
Capacitor equals RC. So you got the resistance times. So it's just the opposite of the inductor. So we can be so you got so T here is L divided by R. So if for capacitor is time constant equals R times C. Okay.
Okay.
So it's yeah, the inductors, it's just the opposite of capacitor.
Is it still 5 time constants to get the capacitor fully charged?
Yes. So because at 1 time constant, which is about 3 milliseconds, is only charged up to 63.2%, according to the graph that we just looked at earlier this year. Okay, it goes up to, so at this is right here would be the 3 millisecond would be here. And then after that will be 6 millisecond would be here. And then 9 microsecond would be here, millisecond. And then 12 millisecond would be here. And then after that, and then 15 millisecond would be right here, would be at maximum at 99%, 99.6. So we can never get into the ideal, which is 100%. So that's the best that we can do, up to 99%. That's fully charged.
Thank you.
You're welcome. Okay. All right, next set. Okay. A series RC circuit consisting of 4.7 microfarad capacitor and 4.7 kilo ohms resistor have a time constant of. Okay, so this is what we just talked about. The time constant equal R times C. So the R is 4.7 kilo ohms times 4.7 microfarad. And so T would be equal 0.02209 second, which equal to 22.09 millisecond. Okay, so the answer is A as an apple for 16. Okay, 17. The circuit current in RC circuit is the circuit current is started at maximum at the beginning because they charge up quickly. At the beginning, as you can see right here, the charge up here goes to even up the first time constant, it goes up to 63%. That's that's pretty quick. from here to here, it's only like 23%. So it's the capacitor is starting to fill up. So therefore, it's only have a little bit room left over for the next one, for the next set. And then after that, even smaller, getting to a point once it's full, and then the capacitor would stop charging. Okay. So therefore, it's maximum at the beginning. So maximum beginning of the charging time. So A is an apple for number 17. Okay, for 18, a series RL circuit of 22 millihenry inductor and a 3.3 kilo ohms resistor have a time constant of, so the time constant equal L divided by R. So L is 22 millihenry divided by 3.3 kilo ohms. So so 22, so milli is 10 to the negative 3. And so divided by the quantity 3 times 3.3 times 10 to the positive 3 for kilo. Okay, so now we just combine. So now we just kind of get the 22 divided by the 33, and we got the 10 to the 3 negative 3 divided by 10 to the positive 3. Okay, so now we just regroup them. So the so 22 divided by 3.3, that's 6.67. So this is 10 to negative 3. So we move the positive 3 to the top, it will become negative. So this is 10 raised to the quantity negative 3 minus 3. So therefore, that's come to 10 negative 6. Okay. So 10 is negative 6. That's same thing as micro. Okay. So that's 6.67 microseconds. So the answer is C as in cat for number 18. Okay. Any question number 16, 17, or 18?
Can you zoom that page out for a full caption?
Okay, hold on. Let me see. Okay, so okay, is that good? Let me a little bit more. Okay.
Thank you.
You're welcome. Move this one back down just a bit so we can see the rest of that. Okay, hopefully I make it clear for you guys, and so hopefully this one give you a better understanding how the time constant is in your circuit, in the RC circuit, as well as an RL circuit. Okay. So any other question before we proceed on forward? Okay, no question. All right, back to you, Mr. Pham. Thank you.
Okay, thank you, Sam.
You're welcome.
Okay, let me get into my iPad. Okay, yesterday we already talking about very basic for the radio frequency. We don't care that. We don't care that one. Okay. One thing you have to memorize, okay? And basically, you can get this a square wave. And basically, square wave could be just a combine of the sine wave at the different harmonic. Okay, so square wave, including too many sine wave inside with a different harmonic. Okay. And now you can see they get a square wave, 2 volt peak to peak. This is the display on oscilloscope. That will be T. That means the time domain. And also the same signal will be displayed on the frequency domain. You can see this will be F in kilohertz. That's what we're using the spectrum analyzer. Okay, and you cannot see any more square wave, but you can see at the first fundamental of first harmonic, they just telling you what is the value. That means what at the one frequency, 1K, then value will be 1.27 V peak. And the next one will be third harmonic. They're not using even. Third harmonic will be 3 kilohertz. And the value will be 4.24. Fifth harmonic, seventh harmonic, and keep going. And you understand it's scope is easy to buy. Cost 1,000, 2,000 or 3,000. However, spectrum analyzer got around 24,000.
And Mr. Pham, where did you get, where did those numbers come from? Is there, maybe I forgot something. Is there a formula or something? Like 1.27 and 0.9?
Oh, that's a display.
Oh, that's a
display on the spectrum analyzer.
Okay.
Not formula, not calculation. Okay. That's a picture from spectrum analyzer.
Okay, then if I could ask you, one of them says, say like the third one, it says 424 millivolts VP, and above that it says 0.1 volts. So how does that work? They just broke it down in that form or what?
No, I don't understand that. Okay. When you're working on the spectrum analyzer, so you will find out what they say 1.27 volt peak or 0.9 volt. Okay. How the relation between those two numbers.
Yeah, that's what I don't understand.
Yeah, maybe they can be an average voltage.
Okay.
Okay. The thing is, you can calculate when they say volt only. That's not a VIMF. That normally will be the average.
So you would take the 1.27 and multiply it times the 6.636, which is the average.
Maybe you can try.
Okay, I won't hold up the class. I'll try to research it myself. Thank you. Thank you.
Yeah. This is the same. Just display. Okay. On the spectrum analyzer, 1 kilohertz. Square wave, 100 millivolt per division. That means you get a 500 millivolt per division. Then you can calculate to see what the V peak to peak. Now, also, this is really need to understand. You get a square wave oscillator. That means if you connect to the generator, you set square wave generator, a square wave 1 kilohertz, then you can see, you can get very too many, okay, signal for 1 kilohertz. And now, basically, what they want only 3 kilohertz to go. And the other, lower, higher, they want to block it. That's what they have to using band pass filter. You guys already learned it. Band pass filter. Okay? That means the center frequency will be 3 kilohertz. And you can get cutoff, lower cutoff, higher cutoff. Okay, after the lower higher than the higher cutoff, they don't want that signal anymore. And now they display on the spectrum here. You can see that they can get a 1K, 2K, 3K. And the 3K, you can see the signal will be can pass through it. Okay, outside that thing, they will be blocking. That will be so on spectrum analyzer. Okay, and electronic communication everywhere. You can got the TV broadcast, listen to radio using your telephone or remote control and more. Okay, so basically in here they given you the simple picture how the signal transmitted over the air. This is a microphone. Okay, your voice will be converting to electrical wave. Your voice will be sound wave, and job of the microphone converting the sound wave to electrical wave. But that signal will be a very, very small. So they need an amplifier to bring it up. Do you know how come they need the voltage amplifier to bring it up? Why? Why do we need it? If you don't need that, what happened?
Are you thinking, Mr. Pham, you won't be able to hear your voice because the human voice is a really low frequency or something like that?
Now the thing is, the signal will be very weak, too small. And if that signal is too small, when they go into the system, they cannot work it. So that's why they must amplify it. Okay? To a certain voltage, they can be working with the system. So that's why they have to get the voltage amplifier. Then they get a power amplifier. And then they go to the antenna to transmit it over the air for transmission. For example, in radio, okay, signal basically transmitted over the air. And this is your radio. You have to get the antenna anyway. So the signal from antenna will be go into the radio. And also they need the amplifier. Then they go to the power amplifier and they can go to the speaker. That's just a very, very basic, okay? A microphone is a type of transducer. It's converting a pressure variation in a sound wave into electrical energy. That's what they're talking about, microphone. A transducer is any device that converting one form of energy into another. The transmitting antenna converting amplify information signal into a new form of energy capable to traveling through the space. Okay, this new energy equal electromagnetic energy or radio wave. Electromagnetic energy consists of two fields, a voltage, okay, or electric field and a magnetic field. It travels through the space at the speed of light. You know, the speed of light will be 3 times 10 to the 8 meter per second. Okay. So basically, your voice sound wave very low and also very low frequency. What the frequency for the voice?
10 to 30K?
That will be 10 to 20 kilohertz.
Oh, 10 to 20?
Yeah. And that signal cannot transmit it over the air. Why?
You need a really long antenna for that.
That means the wavelength is too low. Occupy most of the space. So that's why cannot. The thing is you understand the wavelength. Same thing as like a period. Period, that means on the time domain. So wavelength on what domain?
Time domain.
Time domain means period. However, wavelength
Is distance.
on what domain?
Distance.
Distance. Correct. Distance. So if they distance, okay, so if they too long, so they cannot be transmitted.
And the distance is a reference bandwidth, correct?
No, it's not a bandwidth.
Well, if it's reference to distance, doesn't it need something to just bounce off of in order to get a return or some type of signal reference?
Now the thing is, let's see. You can say they draw this way. That will be distant. Okay. And that will be a wavelength. Okay. So if the wavelength is too long, so if they transmit it over the air, okay, they cannot. The thing is, if you get a very, very big, long distance, you know, the wavelength, so they could be screwed up, everything cannot be transmitted. Now we see in here, you can, hopefully you can understand a little more. Radio transmitted antenna need to be at least 1/4 of wavelength. Okay, radio transmitting antenna. If you want to make antenna, then you have to understand on this one. Audio frequency are those we can hear. They are 20 to 20,000 hertz. An audio frequency that is in the middle of our hearing range is 1,000 hertz or 1 kilohertz. That's for audio. Let's calculate the wavelength of a 1 kilohertz electromagnetic wave. Lambda equal V divided to F. V will be 3 times 10 power of 8. That's the speed of light. Divide 1 kilohertz. You get 300 kilometer. That's the wavelength. So now if you want to make your antenna, you divide by 4. So your antenna will be 75 kilometer. No way you can make it. So now you understand the relation between the wavelength and antenna. Okay, make sure you understand. That is the way. In order to make the antenna, they have to be at least 1/4 of wavelength. Increase frequency, always decrease wavelength. Decrease the frequency, always increase wavelength. That's easy to understand. Let's try changing 1 kilohertz to 10 kilohertz. Then you can calculate lambda, they will be equal 30 kilometer. And the length antenna now will be 7.5 kilometer. So you want the short antenna, then the frequency must be high. If frequency 150 megahertz, then that will be telling you antenna will be just 0.5 meter. So now you will see the relation between the frequency, okay, and the length of the antenna. 100 megahertz signal may be transmit just fine. But there's one more problem. We cannot hear 150 megahertz. The thing is, it is too high. Okay? This is a solution. You can see, they can tell you the signal can be transmitted easy at 150 megahertz. However, you cannot hear signal from 150 megahertz. Okay? So that's why they say this is a solution. It is called a modulation. When we modulate a wave, we place a low frequency information signal onto it. The low frequency signal is just along for the ride. It is in effect carry on the top of the frequency signal. The high frequency signal is therefore we call a carry. So now basically you understand your voice is low frequency. Okay. However, if you want to transmit it over the air, it's hard to do it. So that's why you want to transmit at 150 megahertz, for example, and you get a problem where we cannot hear at the frequency 150 megahertz. So now what they want to do, they want to get another signal, try to carry your voice over the air. Okay, that's what they call a carrier. Many mobile FM radio units operate near 150 megahertz. At this frequency wavelength, they can get 2 meters and L minimum. That means they can be 19.7 inches. Frequency above the range of hearing are called radio frequency. Any frequency above 20 kHz is considered a radio frequency. Okay. Now we'll see example. What is the wavelength of 710 kHz AM broadcast signal? Okay. So if you want to calculate that, easy, right? They will be equal 3 times 10 power of 8 divide 710 kilohertz. You can get 422.5 meter. Okay. What is the minimum height of the antenna tower in feet if it is 1/4 of wavelength long? So basically you take that wavelength divide by 4, you can get this is your antenna will be 346.6 feet. Okay. A quarter wave, lambda divided by 4, quarter wave, with antenna measure 108 inch. What is the approximate operating frequency of transmitter? Okay, let's see how they do. What? Lambda divided by 4. That's a quarter. Okay. Divide times 1 meter, divide 39.378. You get 2.74 meter. The wavelength is 4 times lambda divided by 4. Okay. So 4 times 2.74 right here. You get 10.97 meter. And the frequency will be equal 27.3 megahertz. That means on this example, they just try to calculate the approximate for the frequency of the transmitter. It's sometimes that go into too much detail here. There are 3 ways we can impress information onto a carrier. First thing, we change the voltage or power of the wave in step with information. This is what they call amplitude modulation. We get three different ways. Okay. First thing, AM means amplitude modulation. That means they change the amplitude. Second, we can alter the frequency of the wave with the information. That's what we call FM, frequency modulation. You see the difference between AM modulation, FM modulation. AM modulation, that means they changing the amplitude of the signal in order to transmit it. FM modulation, they will be changing the frequency of the signal, okay, for transmitting. And the last one, you can change the phase of the carrier wave. That's what we call phase modulation. So basically, you get the three basic modulation: AM, FM, and PM. AM means amplitude will be changed. FM means frequency will be changed. And the PM, the phase will be changed. Okay? A practical radio system. Every radio transmitted is assigned to operate on a specific carrier frequency. The job of the carrier oscillator is to generate this frequency. You want this oscillator. You can go to the store, electronic store, to buy oscillator. However, when you buy oscillator, they will be asking you what frequency you want. You can say 1 megahertz, okay, or 10 kilohertz. That's a very simple, okay. When you connect power into that oscillator, they will be generate the output for you, either 10 kilohertz, okay, or 1 megahertz, any frequency you want, okay. The purpose of an oscillator is to convert the DC from the power supply into the AC signal. The output of carrier oscillator is a nearly pure sideways. The modulator has two inputs. First, the radio frequency sideways from the carrier oscillator. And the second thing, the information signal. What is the information signal?
Voice.
Who can tell me?
Voice.
What is it? What is the information signal?
He said voice.
It's your voice. It's your voice. Okay? So that is, you have to understand the modulator. Modulator, they get you input. One from oscillator. And another one will be from your voice.
Question, Mr. Friend.
Yeah.
On the top, it says there are 3 ways we can impress information onto a carrier. Now, from what I understand, the voice signal is riding on top of the carrier wave.
No, we're not going into that detail yet.
Right, but this is my question, and maybe you might be able to answer it at a later time. What is the name of the space that the information signal is writing in? Not on top of the carrier, but there's a specific name where that voice signal is writing. What's the name of that space that's on top of the carrier?
No, that depends on you using AM or FM or PM. Right now,
Was he talking about the envelope?
yeah, that's what I said. Now we still on try to identify, can you understand what is the AM modulation, FM or PM? The thing is you already got few things. Okay, that will be confuse the other. When we act up to that point, you can add. If you say, you know what that means for AM modulation, that means amplitude will be changing. FM means frequency will be changing. Or PM, the phase will be changing. That's the first thing definition. Second thing, they're talking about modulator. And now we concentrate on make sure you guys can follow it. The modulator has two inputs. One will be from oscillator and another one from the information signal. And I already explained to you oscillator. And information that's just your voice. Okay? And the output of the modulator circuitry, that's what they call a modulated carrier wave. Basically, that's a very basic definition. If you don't understand on this thing, cannot go more. When we're talking more about modulated carrier waves, you don't know what that means. They will be combined. Okay? Signal from oscillator and the information means your voice. They combine together. And that's why they call it modulated carrier wave. So you got any question on this page, just go ahead and add. This is very, very good to help you to understand about radio frequency. If you go into the bookstore to buy a book, a textbook, I believe you read it, you cannot understand at all, either myself. I get one book very detailed, very good. That means very simple explanation for technicians able to understand. Mr. Smith bought one, right? Okay, any question on this page? Now, see what they said here. The thing is we don't have any screen, any tab on this section. So that's why. If I can give you the answer for you guys to read. What is the purpose of an oscillator circuit? The job of carrier oscillator is to convert the DC from power supply into the AC carrier frequency. Number two, how does an RF amplifier differ from an RF amplifier. That means the difference between RF and AF amplifier, radio frequency, okay, and audio frequency. RF is a non-linear amplifier, and AF is the linear. We're talking about linear and non-linear amplifier. Number 3, what is the purpose of the modulator circuit? The purpose of modulator circuit is combine the carrier oscillator and the information. That's what they call a message, or that's what we call your voice, to produce a modulated carrier wave. You understand, you have to keep reading over and over. How many radio signals can be expected in the antenna circuit of the receiver? The answer will be 1,000, too many. Number 6, how does a radio receiver select one signal from 1,000? The answer will be use LC resonance circuit. You already know resonance. Okay? Resonance, that means when you changing LC up to the resonant frequency, what you get?
Hey, Mr. Pham,
If at resonant, what you get?
Mr. Pham.
Yeah.
Okay, so if I could just go back to 4 just for a second. Okay, so you got a bunch of signals or whatever coming in on the antenna. And then down to number 6, with all those things coming in, you have to use the resonant frequency to tune in, to fine tune so that you get what you really want. In other words, you don't want all of them, you want one station or whatever. So you have to tune in, and the way you tune in is use resonance.
I understand. I agree that. However, right now, I want to asking at the resonance, what you get at the resonant frequency, what you're supposed to get.
X sub L cancel out X sub C. They cancel each other out.
Yeah, but the thing is that's not what you get. I want to know at the resonance.
You get the station or the voice or whatever you want to hear.
No. Now we're talking about resonance. We're not talking about radio. I'm talking about resonance.
You get the strongest signal.
What is stronger?
At resonance, your signal is peak.
No.
They filter out all the other signal.
No.
The noise.
No. I'm just talking about resonance. Can you guys tell me at the resonance what you're supposed to get? Get what? I'm not talking about signal in the radio. I'm talking about a lecture we're learning about resonance. You understand that the resonance, that means XCXL equal, right? But I want to ask the guy, what do you get from the resonance? What you want to get?
The carrier signal?
No, it's not carrier.
We're getting maximum current at resonance.
Exactly, that's what I'm asking you. You understand at the resonance for series, resonant frequency, you get a maximum current. When you get a maximum current, what else you get? You get a maximum the power. Right?
Yep.
That's what I want the answer. At the resonance, we get a maximum current. Okay, or for parallel resonance, what you get? Maximum what?
Voltage. Maximum voltage.
No.
You said parallel, right?
Yeah, I'm talking about parallel. What you get? Series, you get maximum the current. Who can answer to me? That's why I said you have to reading over and over and over. If you
Don't you get maximum
listen.
Don't you get maximum voltage?
No.
Okay.
How come I too old and I still memorize? And you guys know.
You've been doing it for 50 years. So what is the answer, Mr. Pham? What's the answer?
That's what I'm waiting. You already know. For series resonance, you get the maximum
Current.
And maximum current, the thing is you get a minimum impedance. And now for parallel impedance, you get the maximum impedance. And you get a minimum current.
Oh, just the opposite.
Exactly.
Okay.
The thing is when you don't want the signal, you try to get the maximum impedance. Okay, what happened in a detector circuit? Okay, it takes the incoming modulated carrier waveform and strip away the carrier. That's a typo, okay? Carrier frequency, leaving a copy of the signal information. Okay, in general, I can tell you.
Mr. Pham, what was the typo or whatever?
Carrier, the carrier, extra Q. Yeah, let's see.
Oh, you mean, oh, it's just spelled wrong, but it's carrier.
Yeah.
Okay, thank you. We got it. We said it's just a typo. That's it.
Okay. So basically, I've been telling you how the process, okay, will be. First thing, your voice, low frequency. They cannot transmit it over the air. So that's why they need the signal they call a carrier. They carry your voice to transmit it over the air. However, when they reach into your radio, so your radio will be trying to remove the carrier and try to get back your voice. Okay? Okay, practical radio system. You can see this is oscillator. This is your voice information. And this circuitry they call a modulator. I already telling you. Modulator get you input, one from oscillator, one from your information or your message. And the output here, what is the name of this output? You can tell me what the name of the output of modulator.
Signal.
And amplitude modified waveform?
Yeah. Output of the modulator, we call a modulated carrier wave. Okay, make sure next time we get a meeting, I will be asking you. If you cannot answer, then I stop. I don't think you guys able to understand, just waiting my time. Okay, again, that's what I keep trying to repeat. Modulator, get a two input, one from oscillator for carrier. This is a carrier signal. The other one will be message or information or the voice, your voice. Okay, then they will be go to RF power amplifier. Then they go to the antenna for transmitting. Okay, and the second one will be a receiver. This is a transmitter. This is a receiver. That means this is your radio. You see your radio get the antenna. How many signals will be on your antenna? The answer we already did, 1,000 or more. Okay.
In the millions.
However, when you tune in your radio, okay, you changing L and C, that they get a band pass filter. They will be allowed only the channel you want to go. Okay. Then they have to go to the amplifier to amplify the signal. Okay. Then they go to the detector, the modulator. Okay. That means they have to take out the carrier to leave on your voice only. And they will go to power amplifier before they go to the speaker. That's exactly the same when you're talking on your cell phone. Okay, so cell phone, your voice here, they have to transmit it over the air. Okay, go to the other phone, the same thing. Okay, they can go through the whole process. Only thing that the different will be different frequency. Okay. Now, making an AM signal. This is an RF carrier. This is your message, your voice. This is a modulator. In the modulator, they get a modulator amplifier. Okay. And after modulator, you can get the amplitude modulated output. So the first stage in any transmitter is an oscillator. This guy. The RF carrier wave contains no information until it is modulated. That means your voice is not in here. Your voice right here. Okay, they will be combined inside here. In order for amplitude to be changed, the voltage or power gain of a subsequent state must be changed. The AM generator has a special amplifier with a variable voltage gain called modulator. The amplifier with a constant gain is called linear amplifier. Okay. The non-linear amplifier is always required to generate AM. Okay, now you see you get the two different amplifiers.
In progress.
Two different types of amplifier. One will be linear and another one will be non-linear amplifier. Now, what you learning in electronics? Transistor, operation amplifier, JFET, you can see they get a amplifier. CCCB amplifier, okay? That amplifier, they get the gain, and the gain cannot be changed. Okay? They get a fixed value. Gain equal 10. That means gain equal 10. No way you can change the gain to a different number. You can change it, but you have to change the value of resistor, okay? Like the gain of the inverting amplifier, RF over R1. If you want to change the gain, you have to change the value of RF over R1. That's what they call linear. The non-linear amplifier, that means automatically the gain will be changed. Okay, so that's why you can see they draw in here, the arrow here. They're telling you the gain will be automatically can be changing. Okay. Now, where is the information in AM signal? The information is carried on top of RF carrier. Actual shape of the carrier is altered by the addition of the information during the process of modulation. The imaginary line that make up this shape are called the envelope. The envelope is a copy or duplicate of the intelligent signal. Okay, let's see, I show you this thing here. Okay, you can see this signal here. Is your voice. Okay. However, the carrier, let's see where I can see the carrier. If you see the carrier right here, that means they just the frequency here, no changing at all. Okay. However, when both combine in the modulator, so you can see your voice, okay, on this side, and this signal here is the carrier. The carrier will be changed with the amplitude of your voice. Okay, you can see that the frequency carrier here. Okay, and that's what they call this one they call envelope. Percentage of modulation and AM modulation index in an AM signal. The percentage of modulation is measure of how strongly the carrier wave is being changed by the information. For radio, the higher the percentage of modulation, the louder the signal will be in the receiver loudspeaker. The variable gain amplifier is a non-linear amplifier. A non-linear amplifier is always required to generate AM, mean amplitude modulation. The maximum percent of modulation will be 100%. A 0% modulation means that no modulation is taking place. The transmitter is said to be dead key or unmodulated. The AM modulation index is the same information as the percentage of modulation. It is given symbol M and H can have a value between 0% and 1 for 100%. When calculate the percentage of modulation in AM signal, we are really calculate the modulation index. Okay, I try to get through this one, then we stop. Remember, the maximum modulation index is 1. That's 100%. A signal that is over 100% modulated is said to be over-modulated, which is an illegal condition. Over-modulation distorts the information and cause excessive bandwidth to be used by the transmitter. Example, what percentage of modulation corresponds to a modulation index 0.5? So percentage modulation equal 100 times 0.5. You get 50%. Definition and measurement of the modulation index. AM modulation index can be defined by the formula. AM, that's what AM modulation index equal VM divided VC. Okay. Where VM is the information voltage and VC is the carrier voltage. Okay. To measure the modulation index on oscilloscope is the following. M equal V max minus V minimum divide V max plus V minimum. I show you on this one. You see that right here. Okay. They will be calculated. You get the AM signal here. Okay. They get the V maximum peak to peak. Okay. That means peak to peak. Read from gratitude of the oscilloscope screen is 5.9 division. And V minimum 1.2 division. Okay. They want to calculate the modulate index. Okay. VC equal V max peak to peak plus V minimum peak to peak divided by 2. Okay. How come they get 7.5 volt? Okay, let's see. In here, 5.9 division. Minimum 1.2 division. And they say modulated in that AM. Okay. Then you have to go. What M equal? Right here. V max minus V minimum divide V max plus V minimum. So they get a 5.9 division. Okay. That means from here to here 5.9. Okay. And minimum 1.2. So what the modulated in that? That means 5.9 minus plus 1.2. Okay, divide 5.9 minus 1.2. And VC means V maximum peak to peak plus V minimum peak to peak divide by 2. Okay, you can see on that one, maybe easy to see on the second one here. Try understand that one. Suppose that AM signal on the scope. So, see, oscilloscope, they say 1 volt per division. Okay, so top to the bottom, how many division? 1, 2, 3, 4, 5, 6. 6 maximum. Okay, this is the minimum here. 1, 2. So 6 plus 2 divide by 2, you get 4 volt for VC. Okay, and VM. Okay, 6 minus 2. Okay, divide by 2, you get 2 volt. So M will be 2 divided by 4 and times 100, you get 100%. Okay, so basically M will be equal VM divide VC. VC, that's the carrier. Okay. VC, you calculate, you get 4. VM, you get Q. M will be equal VC divide VM divide VC. You get 100 times 100%, you get 50%. Okay, so now what you can do, try to read over up until this page. Okay, then we can talking about this more detail next meeting. And also I telling you, next week we get only one day lecture on Monday. And you get the lab will be Tuesday, Wednesday, and Thursday. Okay, try to get as much on the left vote as possible. Today I supposed to teach your guy on the left vote. However, I forgot it. Okay, we go with the RF, so that's why I forget it. Sorry. Okay, so any question? Basically, what I'm saying here, that will be for your guy to try to understand on the RF radio frequency. Most of the company, big company in San Diego, it will be defense company. And a defense company, they will be more working on communication. If you're able to working on this area, then the job very skilled. Okay. The thing is, sometimes people want to learn. However, you can know basically the lecture, but on the lab, no way. You cannot buy spectrum analyzer for 24,000. Or another equipment, that's what we call network analyzer. Got around the same. In this program, in this class, we bought it. The thing is, when I'm working, okay, I'm not working on RF. However, the lab for RF is next to my lab. However, you understand, you work for the fan. It's not your job. You cannot get into that area. However, outside, I can see what equipment they're using, but I cannot exercise or learn it. That's why I bought it for my lab, my program. Only the students show me you're very good and you want to working on that, then maybe I can let you working. Otherwise, you understand the equipment too expensive. Something going wrong, you get a big problem. Okay? Anyway, any question to me? No? Okay. If it's not, then good night, everyone.
Good night, everyone.
Right, thank you.
Thank
You're
you.
welcome. Good night.
All right.